Okay, we've retained another integral. We've got the integral from 0 to infinity of x squared over x squared plus 1, x to the 2024 plus 1 dx. Okay, I think I got the idea from this from a number of videos that I did recently. It's got some similarities. For one thing, we did a video on just 1 over x 2024 plus 1, so that's similar, but there's some other similarities to some previous videos. I didn't really try any other methods on this because I had a way in mind to use those previous results. So to start with, what I want to do is add a plus 1 right there. Doing that so I can get cancellation with this term. Of course, I don't want to change it, so let's just subtract off 1, and then we can break it up into two integrals on the minus sign. But now in the left integral, we can just cancel the x squared plus 1's, leaving a 1 in the numerator. And what you'll notice here, this integral is that exact integral I did in the previous video, just 1 over x 2024 plus 1. And so what I want to do is let's put some labels on things. Let's call this first integral I. Let's call this second integral j. And so to get back to our solution, what we're going to need is we're going to need just I minus j. So let me just clean up the board, and what we'll do is we'll work on these two integrals separately. Okay, so for our integral I over here to the left, what I want to do is use this formula on it. I derived this formula in a previous video. I can give you a link to this one, or also I can give you a link to this video where we just kind of do this out the long way. Now, before I use this formula, it does look kind of different, so I just kind of want to get it into the same form. We've got the bounds all set. On here, we have the exponent on the x, so our a value on this. So our a value in this formula is just going to be 2024. But then we've got nothing here, so if we write this just as a 1 coefficient, then we can just kind of create this b value, so we'll have b equals 1. And then we've got nothing in the numerator, so let me kind of move things around a little bit. In order to create an x term, I can write it as x to the 1 minus 1. That way what we have here is just x to the 0, and this whole thing's 1, and so we haven't changed it. And so doing it like that, our s value is just going to be this piece, so we're going to have s equal to 1. And then so with all of this stuff here, let's take this and plug it into the formula, and then we'll get a value for this in terms of the gamma function. So first, our a value is 2024, so we have 1 over 2024. Gamma b minus s over a, that's going to be 1 minus s over a is going to be just 1 over 2024. And then again, gamma of s over a, 1 over 2024. Then the denominator gamma of b, just gamma of 1. Now for gamma of 1, we've got the formula gamma of n plus 1 is the same thing as n factorial, it's just reducing by 1. So this is the same thing as 0 factorial, but that's just 1. And then in the numerator, you'll notice if you just add these inputs together, they add up to 1, which tells us we can use Euler's reflection formula on it. So for Euler's reflection, we have gamma 1 minus z, gamma of z. We can say the value of this is just going to be pi over sine pi z. So in our problem, the z value is just 1 over 2024. So what we can do on this is write it as 1 over 2024 times pi over sine pi over 2024. And maybe I can just write it a little bit nicer, but this is going to be our exact value for the integral I. Okay, so now moving on to our j integral. This is also one that I've done recently. What I want to do for this one is just let's do a trig substitution on it, noticing as we've got x squared plus 1 here. So that means tangent is going to work well. Let's rearrange this and solve for t. So we have t equals just arctan of x. And then let's take a derivative on this. So for our dt value, we just get 1 over x squared plus 1 dx. So what that means is if I just create a 1 right here, you'll see that everything right here, this is all going to turn into just dt. So then let's go ahead and substitute. So first, updating our bounds, plug in infinity, arctan at infinity is going to be pi over 2. Plug in 0, arctan at 0 is just 0. Then let's kind of create a 1. This here is going to become tangent 2024 of t plus 1 dt. But now kind of an optional step, let's multiply in. I'd kind of prefer to get this into sines and cosines, but you don't really need to, but we can multiply in cosine 2024t over cosine 2024t. That way we're just multiplying by 1. When I multiply in and we rewrite it, what's going to happen, the whole numerator just becomes cosine 2024. In the denominator, cosine, tangent's just sine over cosine, so the cosines cancel and we end up with sine 2024t, and then this is just going to become cosine 2024t. But now this here is perfectly set up for King's principle. At this point, you may have just recognized this form and know the answer, but I'm going to kind of do it out. So what we're going to need on this for King's principle is a plus b minus x, adding the bounds together. So that's going to give me f of pi over 2 minus x. Using the formula, the bounds are going to stay the same. So we're still going 0 to pi over 2. And now when we input this, I actually probably should keep this a t, but it doesn't matter what variables we have. So for f of pi over 2 minus t, when you do that, you're just going to have complementary angle formulas because cosine pi over 2 minus t is going to be just sine of t. And then the same thing is true of sine. And what's going to happen is the exponents aren't going to matter. We're just going to change all the cosines to sines, all the sines to cosines, and just rewrite this. But now what you'll notice is these two integrals are really similar, same denominators, same bounds, different numerators. But if we just add these two together, remember this is our j, and this here is also j. So if I just add these two integrals together, we're going to end up here with 2j. But then what just happened, numerator and denominator is same thing. So the whole integral cancels all the way down to 1. Integrating 1, we just get t evaluated from 0 to pi over 2. Plugging that in, we get pi over 2. Now remember, this is still 2j, so I just need to divide off 2 on both sides, divide 2 here. And so for our j piece, we just get pi over 4. Okay, so now that we have our I minus j value, I'm realizing I definitely copied this down wrong. This is supposed to be a 2024. For a second there, I was going to cancel the pi's out and get a totally different answer, but I think it's right now. So now for an exact solution, this is about as good as I can do. You could factor out the pi in the numerator, but I think I'm just going to leave it. One thing we can do that I think is kind of interesting that we did in the video for this one was the estimate for this. We have this limit when x is going to 0 of sine x over x. This here is a really well-known limit and the value is just 1. Well, what we have right there is a little different. We can kind of rearrange it. I could write it, bring the 2024 into the numerator, write it as pi over 2024 over sine pi over 2024. Now we have the same value here and here. It's definitely not 0, but it's getting kind of close. So as an estimate, we can use this because this is 1, it's also going to be true if we just flip it. So for this limit, this is also going to be 1. So it turns out for this, it's a pretty good estimate to use 1 on this. So for our solution, this is going to be pretty close to just 1 minus pi over 4. And for a decimal solution for this is something around 0.2146. Okay, there you have it. Thanks everyone for watching. Have a good day.